Stars come in all shapes, sizes, and colors, but have you ever wondered how they live and die? In this episode, we will show you the life of a star from its birth in a cold molecular cloud to its death in a spectacular explosion known as a supernova. All stars begin their lives as part of a giant cloud of gas and dust floating through space. These clouds are mostly made of hydrogen and helium, the simplest and most abundant elements in the universe. Over millions of years, gravity causes these particles to clump together, creating dense pockets of gas and dust known as molecular clouds. At this stage, the cloud is not considered a star, but rather a prestellar core or protostar. It's just a baby. As the core continues to collapse under its own gravity, it heats up dramatically due to increasing pressure at the center. This process is similar to squeezing a ball of dough. As you apply pressure, the dough becomes warmer. Eventually, the core becomes so dense and hot that nuclear fusion occurs. Hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy. This is when the star really ignites. The outward pressure from fusion reactions counteracts the inward pull of gravity, creating a balance that makes the star stable. This is called hydrostatic equilibrium. A star is now born. Most stars, including our Sun, spend the majority of their lives in this state, fusing hydrogen into helium in their cores and shining brightly in the night sky. We call this stage the main sequence. Stars like our Sun will spend billions of years in this stage. For the Sun, that's about 10 billion years. Once the star has used up most of the hydrogen fuel in its core, the balance between gravity and nuclear fusion is disrupted. Without the outward pressure from fusion, gravity takes over and causes the star to collapse. As the star collapses, its temperature and density increase dramatically. The core contracts, heats up, and expands again, transforming the star into a giant, cooler, and less dense than before. This new phase is known as a red giant. The star is now much larger. Our Sun is about average size, but some red giants can be hundreds of times larger than Earth. The outer layers of the star expand, cool, and glow red, giving the star its distinctive color. During this phase, stars are still fusing elements, but instead of hydrogen, they fuse helium into heavier elements like carbon and oxygen. The rate of fusion varies depending on the mass of the star. Low-mass stars will spend several billion years in this phase, while high-mass stars move through the stages much faster. Eventually, the star fuses all the available helium in its core and becomes unstable. Some low-mass stars, like our Sun, will shed their outer layers, leaving behind a small, dense core called a white dwarf. These are extremely hot, but only about the size of Earth. Our Sun will become a white dwarf in about 5 billion years. Other higher-mass stars will go through more dramatic changes. Their cores will continue to contract and heat up until the temperature is high enough to fuse even heavier elements. They create elements up to iron. But this process requires even more energy, and the star cannot sustain itself. Gravity takes over and the star collapses dramatically in a supernova explosion. These explosions are among the most energetic events in the universe, releasing as much light and energy in a few weeks as the Sun will in its entire 10 billion year lifetime. During the explosion, the star's outer layers are thrown into space, creating beautiful and complex shapes of gas and dust. These remnants serve as stellar nurseries for future star formation. Meanwhile, the core of the star collapses to incredibly small size, creating an extremely dense object known as either a neutron star or a black hole. Neutron stars are about the size of a city, yet can have a mass greater than our Sun. They rotate rapidly and have powerful magnetic fields that accelerate charged particles to near the speed of light, emitting intense beams of radiation. Black holes are even more extreme. They can have masses of several dozen to hundreds of times our Sun's mass, but are compressed to a sphere only a few miles wide. The gravity near a black hole is so strong that not even light can escape collapsing inward. Anything that ventures too close, including gas, dust, or even light, is pulled beyond the surface, never to be seen again. This boundary is called the event horizon. What happens inside the black hole remains unknown because no information can escape to be observed. Black holes are truly mysterious objects in space. So, which fate awaits our sun? Well, since our sun is a relatively low-mass star, it will eventually become a white dwarf after shedding its outer layers. However, there are many other stars out there that will meet a more explosive end, creating spectacular supernovas and leaving behind neutron stars or black holes. The death of a star is not an ending, but a beginning. The material expelled during the supernova explosion enriches the interstellar medium with heavy elements that were once deep within the star's core. These elements, such as iron, oxygen, and carbon, are the building blocks of planets, moons, and even life itself. After a star goes supernova, the material expelled forms beautiful glowing clouds of gas and dust called nebulae. Within these nebulae, new stars and planetary systems begin to form, continuing the cycle of stellar life, death, and rebirth. Nebulae come in a variety of shapes, sizes, and colors, each with its unique beauty and characteristics. Some nebulae are huge and bright, such as the Orion Nebula, which is visible to the naked eye as a faint cloud in the constellation Orion. Other nebulae are smaller and more complex in shape, such as the Eagle Nebula with its iconic pillars of creation. Each nebula is a dynamic and evolving region of space, where new stars are born and the cycle of stellar life continues. Here are some interesting facts about different types of nebulae. Emission nebulae are clouds of ionized gas that emit light as the gas particles return to their normal state. They often have a reddish color due to the presence of hydrogen. Reflection nebulae, on the other hand, do not emit light themselves but reflect the light of nearby stars. They tend to have a bluish color due to the shorter wavelengths of light being scattered by dust particles. Dark nebulae are dense clouds of dust that obscure the light of objects behind them. These nebulae can have a variety of shapes and are often associated with star formation. Planetary nebulae are not actually planets, but are clouds of gas and dust that have been expelled from red giants or other evolved stars. They often have a spherical or hourglass shape and can be quite colorful. Supernova remnants are the expanding cloud of gas and dust left over after a star explodes as a supernova. These nebulae are highly dynamic and evolve quickly over time. The study of nebulae is an essential part of astronomy, as they provide valuable insights into the life cycles of stars and the chemical activity in space. Astronomers use various techniques to observe and analyze nebulae, including spectroscopy, which allows them to study the composition and temperature of the gas. By observing the changes in nebulae over time, astronomers can learn about the processes that occur during star formation and the evolution of stellar systems. We hope you enjoyed learning about the life cycle of a star and the fascinating world of nebulae. These celestial objects are truly amazing and provide us with a glimpse into the vastness and complexity of the universe. If you want to learn more about space, make sure to subscribe to our channel for more updates on our latest videos. And don't forget to hit the like button to support our work. Thank you for watching, and we'll see you next time. A star's mass determines its fate when it dies. More massive stars have shorter lives and end in spectacular supernova explosions, leaving behind neutron stars or black holes. Low-mass stars like our sun live longer, ending their lives as white dwarfs. Here's a closer look at the differences. High-mass stars have a more dramatic life cycle. They fuse elements up to iron in their cores, and when they go supernova, they create elements heavier than iron, enriching the universe with materials like gold and platinum. These elements are rare on Earth because they're produced in very small quantities in our sun. However, they are more abundant in high-mass stars. On the other hand, low-mass stars like our sun have a more peaceful existence. After shedding their outer layers, they leave behind a small, dense core, known as a white dwarf. White dwarfs are extremely hot, but they are also very small, about the size of Earth. Our sun is expected to become a white dwarf in about 5 billion years. Whether a star ends its life with a bang or a whimper, its death is also its birth. The material expelled during the star's death creates stellar nurseries, where new stars and planetary systems can form. The cycle of stellar life, death, and rebirth continues, and the universe keeps shining. Here's a summary of the main stages in a star's life. Molecular cloud, protostar, main sequence star, red giant, and finally either supernova and neutron star or black hole for high-mass stars, or white dwarf for low-mass stars like our Sun. Each stage is marked by significant changes in the star's size, temperature, and luminosity. Understanding the life cycle of stars helps us appreciate the vastness and complexity of the universe and our place within it. Now check out this video on your screen for more fascinating insights into the world of stars and galaxies. Don't miss out on this opportunity to expand your knowledge and join the conversation. See you there.